We are live. So I think I've heard generally good comments about having the course echoes available, even when you listen to me live. And so I'm going to continue that practice through the end of the semester. The machines are up and working now, which is great, and so I'm going to make use of it. And hopefully we'll have a full set of all my lectures course echoed. We missed two of them. I'm not thinking that's a big deal because one is the physical realizations of AM, of modulators rather, and another one is the review. So if we're going to lose a couple, those are probably reasonable ones to lose. But as long as the machine's up and running, I figured we'd go ahead and keep recording them for your benefit and also for the benefit of future students down the line, hopefully. A couple of bookkeeping things, public service announcement. A week from Wednesday, which is March 5th, our first exam. And it will cover stuff that's now ancient history to us. That's chapters 2, 3, it's a review of signals and systems, and just a touch into section 4.1, by which I mean how a multiplier works. What a multiplier is, how it works. Questions of that nature, particularly from the mathematics of things. I find that also fits well into the property of Fourier transforms for table 3.2, I believe. So review of signals and systems all the way up into multiplication of two signals for the subjects. And even more conveniently, lectures 1 through 9 on course echo. Okay, the lectures 1 through 9 that I've given and are now archived on course echo are the subject of this test. Closed book, closed notes, no calculator. Okay, so everyone says I have to memorize a lot, and my answer is you should figure out what you need to know. Even factors of minus signs, factors of pi, factors of 2, those are not in themselves a real big deal to me. If you get them right, I'm really going to be happy and excited. But you should get them right because you know why a minus sign is there as opposed to memorize it. Okay, because your memorization won't stand up the test of 20 years, but your knowledge of why things happen will. Okay. I've also, in your textbook is Appendix E, and that's a lot of fun math facts, trig identities, some integrals, some derivatives, and things of that nature. And I've Xeroxed those, and I've copied those, and I'll give you those out, and so you can use those. I don't want you hung up on weird things to memorize, like the cosine to the 6th power. There's a good trig identity for that. It's on the handout. Use it there. If you need to, of course, you can rederive it from Euler's relationships and the properties of exponentials, and that's how you'll have to do it if you're, in a meeting on an airplane, a private jet, without all your textbooks or your calculators, 10 years from now. But until then, you can have that at your fingertips. Any questions about the test? Okay, you've all had them before. It is what it is. We do have to have tests for some reason. Probably the best reason is just to give you feedback on how you're doing. And maybe another good reason is a good test will be a learning experience in and of itself. In other words, because there are problems that you haven't seen before and they're written by someone you haven't had problems from before, it'll force you to think about things in a way that, maybe stresses you out a bit, and maybe also gives you a new insight to it. I remember taking tests as an undergraduate and just having horrible experiences for like the first 20, 30 minutes where I'd read through every single problem and I wouldn't know where to begin. And because I had no social life, I stuck around and I looked at it and I thought about it. And bit by bit by bit, I chipped away at it until I eventually kind of, did a halfway respectable job on most tests, and sometimes even better than respectable job on some tests. But so that's a little tip. If you see a problem that you haven't seen before, that means you have to figure it out. It doesn't mean that it's supposed to be in your memory bank and it isn't. It means that you have to figure it out, and what that might mean is a little stress and angst, guessing, trial and error until the dam breaks and the water flows out and your answer is sitting right there. Okay? And that's a lovely experience if you ever get that. So I say that because a lot of times I'll be giving a test, and people will give me a blank piece of paper after 20, 30 minutes. And I try to say, sit down and relax, and maybe something else will come to you. And they don't. So I'm just encouraging you from now, just decide to show up for the entire length of the test and do your best. You never know what's going to hit you 5 minutes from now as it pertains to solving the test. And it would be a shame to be on the other side of the door and having the answer come to you. So just a thought, and that's supposed to motivate you, not demotivate you. I don't know if that's true or not. Today's lecture, we continue in Chapter 4. And I'm going to go through AM, in particular the envelope formulation. I think that's labeled in Section 4.2, and that's DSB. And then if we get a chance, if we get started, if I'm not too long-winded, or if I don't hit a digression, which I don't think, because envelope stuff is kind of boring, I'll get into QAM. And then we'll do a single sideband and then a couple more little topics. And we pretty much finished with AM, well, probably not right before spring break, but maybe right after spring break. So spring break will be a good time for you to get caught up on Chapter 4 before we have a test somewhere at the end, towards the end of Chapter 5, which is FM. Okay? All right. So we're going to look at we know that when we consider amplitude modulation, we know that the idea is to use a carrier frequency, an omega C of t, a local oscillator that's a nice pure sinusoid. In this case, a cosine. We're going to be careful in a little bit more, especially when we get into QAM, about phase. But for now, we'll just call it a cosine. And we know that we want to mix or combine our message signal on top of that cosine. And so we do that. We use a mixer, a multiplier, and we have m of t multiplied by cosine omega t, ct. And we know, we've talked a lot about what happens to that in the frequency domain. I'll go over that a little bit more detail in a second. But basically, whatever shape frequency domain I have of m of t, once I multiply it by a cosine omega ct, I move that shape out to the carrier's omega c, the carrier frequency omega c. So I'm no longer talking about my message signal at baseband, say 500 hertz. I'm now talking about it at the carrier frequencies plus and minus 500 hertz. So maybe 100 kilohertz plus or minus 500 hertz instead of baseband. And we do that for a couple of reasons. Does anyone remember the two reasons why we want to modulate and why we want to use the carrier frequency? Yes, sir.
Noise and physics of propagation.
Okay, so the answer was, the first answer was noise. So I'll pause you right there and say, what about noise?
At lower frequencies, the noise energy levels are higher.
Generally speaking, the power spectral density of the noise, the energy levels within a particular band of frequencies, is higher for low frequencies than for higher frequencies. And so if we go to high frequencies using a carrier, we get out of the shadow of noise, and our signal-to-noise behavior is much better. And that's true for AM, and it's also true for all instrumentation. All instrumentation. If I continuously pulse an input signal into a system under test, I generally do much better in my detection. Okay? Now you also answered the second part of the question very well, so I'll go back to you and say, what was the second part? The physics of propagation. That sounds correct and a little bit vague. Can I push you for more details on that?
Okay, so I remember you saying, like, when you have a very a slower frequency, like the size of the antenna you need would be incredibly large.
There you go. That's a good example. In general, and you don't know this yet, even if you're taking EMAG now, you don't know this yet, but you kind of do from common sense and from maybe learning your electrical engineering a little bit off the streets of Dallas, the rough streets of Dallas, that your antenna scales with the size of your wavelength. So the shorter the the slower the frequency, the longer the wavelength, meaning the bigger the antennas that you have to deal with. And it turns out that one of my favorite little mnemonics to remember is a gigahertz, a nanosecond, and a foot. Okay, so a gigahertz and a nanosecond does 1 over, and a foot is the length of space that a light wave goes, or an EMAG wave goes in a nanosecond. So a wavelength of a gigahertz signal or nanosecond period is 1 foot. And that's a nice, reasonable number to carry around in your head. And so if you have a cell phone that operates at a couple gigahertz, your antenna is measured in inches rather than at baseband, which would be in terms of kilometers or miles. And all of a sudden, you can imagine inside your cell phone, your smartphone, some shape of antenna that fits in your hand, as opposed to something that you'd have to pull out. If you remember the old brick cell phones, that you'd have to pull out that antenna. And then if you went even really much slower, boy, you'd have to be pulling that out for a long time to get an antenna worth a darn. Okay? Any other examples of that physics of propagation business that he used?
The atmosphere?
Yes, the atmosphere or the channel that you use might behave differently at different frequencies. For example, optical signals might go really, really well through glass. Electromagnetic signals may or may not go as well through that dielectric. The channels can be smaller as your wavelengths get bigger and bigger. That's certainly true of glass versus free space, versus optical frequencies versus radio frequencies. And sometimes there's certain bands that are somewhat forbidden, such as terahertz radiation, millimeter wave, terahertz radiation. That stuff gets absorbed by almost anything, and so it's like sending a signal through a brick wall. It just eats everything up, and it's just really hard to propagate. People are trying to figure out how to use that, and it's an exciting area of research with some production, not the least of which is that they think they can see through brick walls with that radiation. But you by picking your frequency of your EMAG signal, you change a lot. The other thing I'll point out is, the physics of a voice versus the physics of electromagnetic is very, very different. If I wanted to go into space, and maybe that's what you meant by atmosphere. If you want to go into space, you can't send sound. You have to beam a radio wave because sound requires an atmosphere so that you have the pressure waves that propagate there and back. Okay? So this is the fundamental thing. This is a fundamental view of what we've been thinking about in terms of amplitude modulation. And now I'm going to change things just a little bit. I'm going to add. And I'll clean this up for special cases a little bit down the line. I'm going to add a term here, and that term is not time varying. That term is not time varying. And so this term here is going to be a DC offset. It's going to be a DC offset to my message signal multiplied by my cosine. Okay? And what that allows us to do is that allows us to look into an envelope approach to AM. Now, this is in the time domain, and I'm going to start to try to adhere to Latti's notation and keep things kind of consistent. So this message signal that comes out of my transmitter, I'll write that as a sloppy phi, AM, as a function of time. My message signal is M of t, M for message. That's not too much of a stretch. And so this is the form of a typical AM signal. And what I want to do is I want to find the Fourier transform of that. And who wants to? Does anyone want to guess, or want to intuit, or want to tell me what that Fourier transform is going to look like? And I don't mean for you to pull out your definition of Fourier transform and work through integrals. This is just sort of an issue of moving quickly from the time domain into the frequency domain, something we've sort of started to practice since day one of our lectures, right? Great. So you want to attack this DC offset, right? And so if you distribute this A times the cosine omega CT, that's a simple Fourier transform that tells you you're going to get delta functions or spikes at plus or minus omega C. So I'm going to write that. Like that. Okay? And I'll sketch it in a heartbeat in a second, just so you'll see what it looks like in the time in the frequency domain. But that's this part of it. Now, who wants to let me know what if M of t transforms to our capital M of omega? That's a notation we've used time and again. So I'm going to start holding your feet to the fire a little bit on that. So how do I write the second term in the Fourier space? If I have M of omega, capital M of omega for M of t, what is the Fourier transform of M of t times the carrier? Have I changed the shape of that frequency distribution? Have I changed the shape of the frequency distribution M of omega? No. So my little mountain peaks that I always draw will stay the mountain peaks. Have I changed the location of them? Where are they now located? Centered on the carrier frequency. And so I can write this as, and there's a factor of 1/2 in there because I'm on both sides of the plus and minus. I have this capital M. So I have a capital M, but I have to shift the frequency like that. Okay? So this tells me that my capital M stays the same. I have two of them, and then one's north, one's to the right of the axis, and one's to the left of the axis. I have two of these, each worth 1/2 of what I had before. And the position in frequency space has shifted over. A simple shift in frequency over. That's what this means, and that's what we've looked at a couple of different lectures from that by now. And so we should start to get a little bit more comfortable with that transformation. Okay. So this so the envelope. So this envelope is the magnitude of this A plus M of t. So that I'm taking A of M of so on the actual signal itself, I'm shifting it up and down. I'm shifting the cosine up and down by a DC amount, and and the shape of the distribution, the shape of the time signal, how that, I don't know how to say it other than how the cosine omega CT is modulated. The envelope of that is proportional to the M of t. And again, I'm going to back this up in a couple of minutes with some pictures, both in the time domain and the frequency domain. But for now, let's just work with this. And so what this means is detect the envelope to get M of t. And we talked about rectification as a way of doing that, a simple diode as a way of doing that. Okay? We've already kind of gone over that in the last lecture. Now, a couple of obvious things. For this to be any use, practically, maybe not mathematically, but practically, we want the carrier frequency to be much bigger than the biggest bandwidth, the highest frequency bandwidth of our signal. And let me, in fact, get this units right here by putting B if B is in hertz and omega is in radians per second. I'll write a 2 pi in there. And then I also want this A plus M of t to be greater than or equal to 0. Otherwise, I have something called overmodulation, and that's bad. And I'll show you exactly why that's bad in a little bit. Okay? Before I do that, let me just mess around with the signal a little bit more. Here's the carrier. And here's the sidebands. Okay. That's the carrier and that's the sidebands. And this is where the information is. And to some extent, this is what we might call overhead. Something that we have to broadcast, power that we have to transmit in order to get the nice physics of transmission and to get the noise behavior that we want. We need this in there. We don't have a way around it. But unfortunately, this is where the information is, and this is the price we pay to transmit the information. Okay, so that's sort of the overhead. So, and think about it, there's no information in the carrier itself. It's just a tone. So it's not. It's really, with maybe the exception of the phase of that carrier, there's very little information to actually use, and certainly the phase is only useful to recover certain things about that. So what we might think about is we might think in terms of the power of the carrier and the power of the sidebands. And that's how much hot water I have to heat up per minute to broadcast the carrier, and how much water I have to heat up per minute to transmit the sidebands. I'm not trying to put this into a wasteful perspective. That I'm going to spend power here and here in order to send information here. Okay? And so if I remember my formula for power, and this is a little bit of a review. I square whatever signal I want to take the power of. I integrate across some period or some long period of time. And then I divide by that time to go from joules to watts. And that's equal to A squared over 2. And I can't really do too much with the form here for the sidebands, other than just to introduce you to some notation, which is just the average level of the signal squared divided by 2. So this integration over time is just an average over time, and that's what those brackets mean. Okay. When you do quantum mechanics, you have bra and a ket, and so bra kets become two entities, two vectors. So another notation that kind of will come up in your experience the next few years. So let's talk about the efficiency, and that's the useful power divided by the total power, and that's going to be the power in the sidebands divided by the total power, which is the power in the carrier plus the power in the sidebands. And that'll be the efficiency.
Where's the variable for the beginning of that?
This guy here?
Yes.
Oh, I was going to comment on it. That's an eta. That's a Greek letter eta, lowercase eta. And I and many other people, not everybody, but I and many other people use eta for dimensionless quantities like efficiencies. Okay, so it's a pretty common notation. Not universal by any stretch of the imagination, but it's not uncommon to use that. And I usually will. So if I forget to say that, I think I heard a mutter of protest when I ripped the paper out.
How the letter looks printed? Like
It's an N with a sloppy tail on it.
oh.
And maybe there's a better way of writing it. Better penmanship, but that's kind of what I do. I'll write it bigger. Okay? That's pretty passable. You might go to a Greek font, especially in LaTeX, that gets it right, and see that. See, if you still had back in the old day, we would get the CRC Handbook of Math tables. And they would even have a Greek alphabet in there, and maybe even some other alphabets in there too. Now, I want to put some pictures to this. Okay, I want to put some pictures to this. I use the term sidebands, for example, and I use the term carrier, for example. And we talked about what this would look like in the frequency domain. So my first order of business is to draw this in the frequency domain. And I'll just remind you that here's my m of omega. And this is 2 pi b. And so this will Fourier transform to that. Now, I think I can slide this underneath here, and not quite. Okay. So this term here, m of t cosine omega ct, transforms, we said, into this guy here, which is exactly what I wrote here. Add to that the DC offset term, means that I have a little spike that comes up on top of each one of these. Okay? So here's the sidebands. And this guy here is the DC. Well, it's actually the carrier. It's actually the carrier. So that's the carrier. So when I do this efficiency calculation, what I'm really asking for in the frequency domain is how much power is located here versus in the sidebands. And I adjust that exactly through A. The taller the A is, the bigger this term is relative to this term. The taller A is, the bigger this term is relative to this term, and therefore the higher this spike is relative to the sidebands. Okay? And we'll be even more specific about that.
Does that mean it gets bigger, the DC or the carrier gets bigger while the area of the MT gets lower?
So take a look at let me take a look at my power in my carrier. Scales as a squared. So the bigger the A is, the more power in my carrier is, the bigger this spike goes, the higher that spike goes. Separately, because I'm adding these guys together up in here, separately, the magnitude of my sidebands is just the magnitude of m of t squared over 2. Okay? So the relative, as I change one, the other stays the same, but the relative amount or this ratio changes. Okay? Now the other thing I kind of wanted to do on this was just let's figure out a nice block diagram for this. And what I want to do here's my message. So here's the signal that that leaves the transmitter. So I need some things in there. I need a carrier frequency in there, a local oscillator. I need a mixer, a message signal, and I need some way to get an A in there. So let's think through this. I guess I'll start with the local oscillator, cosine of omega CT. And how many times do I use that in the formula? Once or twice? Twice. Once for my offset, my carrier, and once to mix or collide with my message signals. So let's take care of this guy first. Okay? So I'll take a lead off of this. And how do I perform that multiplication or that mixing? I use my little block with a multiplier in there. And I somehow get my message signal and I feed that into there. So I look through, I gave you about 3 or 4 different ways of realizing a mixer. So there's others out there, so you'll look through your inventory of parts, and you'll pick that mixer that works, and you'll wire this up that way. Block diagram is a little bit sloppier, a little bit more schematic. And what I have here, at this point here, is this term here. I have to sum these two terms together. So I might as well take this into a summation. Since I know I have to sum it to something. So now I need to come into the other end of that summation. Since I have this term here, I need to do something about this term here. So somebody said I needed 2 leads out of my local oscillator, so I'll draw the other lead. And what should I do between those 2 wires? I need to scale by a certain amount A. So I'll make a little amplifier in there. Okay? Now this block diagram really doesn't amount to a hill of beans. It's not that necessary. But the exercise in constructing it that we went through, slowly thinking it through, each term of the equation and how it might look on a block diagram, that's of course a skill, and I mentioned this, that's a skill that I really want you guys to become facile with. I want you to be very, very comfortable with that process. Both not just reading this block diagram and writing the math from it, but also going from math to that block diagram. That's one of those underlying skills of this class that I hope to kind of impart. Now let's go into some of this other stuff, like overmodulation, things of that nature that I sort of put in there and left you hanging, which of course is one reason you didn't walk out on the lecture, because you wanted to find out about overmodulation, remember? Let's look at that for a special case. And so special case of tone modulation. So I have M of T and you can think about this as testing your system. Since you know that your message signal is a summation of Fourier components, of a Fourier series, now what you're going to do is you're going to set your function generator to just one of those Fourier components. Maybe the 447 Hertz component, which is what frequency? Somebody knows that. I don't. I keep forgetting. But so maybe an A sharp or an A flat or some chord that's standard in music. And you dial that into your function generator, and you take this. Now notice that I have the same A, and I have now a mu. And so I've scaled this. I scaled this so that I can write So I have omegas of m, the message signal, and omegas of c, the carrier frequency, and I have the amount of mu. Notice that cosine goes between -1 and 1. And so mu is actually the strength of that cosine, scaled the strength of that cosine. So that mu, if that mu is 0, I'm not broadcasting any message. If that mu is equal to 1, then I'm perfectly matching this one here. If mu is equal to 0.5, I'm undermodulating. And if mu is equal to greater than 1, I'm overmodulating. I'll give you some examples of that in a second. So mu, for good operation, and if you need a name for this, we can call it the modulation index. Mu should be between 0 and 1 for good operation. And let me show you why. This plot is on my webpage. And what I have plotted here is exactly this function, 1 plus mu cosine omega m omega ct. There's not much of a difference between my omega c and my omega m. Here's my envelope. Here's my envelope, and my envelope is governed by omega m. You can see maybe 5 cycles of omega c, which is this frequency, make up an omega m. So omega c may be 5, 7, I forgot what I used to plot this, but not a little bit, maybe 5 to 10 more than my omega m. And what I've done is I have mu equal to 1/2, mu equal to 1, and mu equal to 1.5. So undermodulated, threshold modulated, or critically modulated, and then overmodulated, if you believe my. Okay. So for the undermodulated term, if mu is equal to 0, by the way, I don't have any envelope. It's a flat envelope. No information is being sent, and so it would just be a straight line of a cosine all the way across here. If I have a little bit of a mu, you can see an envelope start to be modulated on there. So the higher the message signal, the lower this envelope is. The closer to the 0 value it is. Okay. If I have mu equal to 1, you can see that I go down, my envelope goes down, and now you can see it just touches. It just touches 0 right there. And then it comes back up. Okay? You can see it just touches. And what's happening there is that mu equal to 1, this -1 and this -1 here is canceling out so that my total signal is 0. And so sure enough, at that point, the green line pops right to 0. Just skims right into 0. And what that means is that instant of time, that infinitesimal instant of time, absolutely no power is being broadcast. There's nothing on that airwave for that little piece of time. Okay? If I overmodulate, at first you sort of shrug your shoulders and say it looks a lot like the blue line, but it isn't. Because look what happens here. Each of these guys go down and then up, but look at what happens right here. The undermodulated cases goes up, the critically modulated case goes up, but because I have a mu equal to 1.5, I have a minus sign in there, and I see this flip. It's called a phase reversal right there. There's a phase reversal right there that'll ruin your entire day. Because that phase reversal means you have a complete discontinuity in your frequency content, and whole bunches of new harmonics are going to be generated right because of that phase reversal. So you will suffer huge amounts of harmonic distortion for this tone modulation system because you've hit a region where you overmodulate. And it only gets worse. You see how this guy is out of phase from the other guys? The overmodulated case is north of the axis, while these guys are south of the axis. That means that we've suffered a phase reversal, and we're not transmitting the same signal that we wanted to transmit. Yes, sir?
So, periodically in that period of time
from, say, there to there?
You just use like no signal really at all?
No, you're broadcasting something. You're broadcasting the information, and a lot of energy has been shed also into harmonics that are completely distortions, that are complete distortions. Most of them are in the band, and so it will come across as, you want a nice perfect opera singer with one frequency. Well, now you've got a ton of harmonics. It's very analogous to a speaker running out of room and giving you a sharp cutoff, a sharp discontinuity in amplitude, in this case in phase, and you generate whole new frequency contents, and that's bad, bad, bad. And the next thing to do, and I didn't do this, but you might do it, and you might even post it, is to take the signal and make it run long enough, and then do an FFT of it. And you can see that you'll see the generation of new frequency components for the overmodulated cases, and not for the undermodulated case. That's a nice little numerical experiment that you can do either in Excel or in MATLAB. I did all that in Excel just because it was, I guess I was traveling at the time and I just had that access to that program. And Excel does a great job of FFTs as well. Just have to find the command and use it. Let me just show you this one other thing here. Remember we talked about the frequency? The efficiency? And the efficiency was the power in the carrier. Power in the sideband divided by the power in the carrier plus the power in the sidebands, the total power transmitted. Well, now we can actually do a formula for the power in the sidebands. Because the power in the sidebands is a nice harmonic, and that's going to be equal to mu A quantity squared over 2 times 2, which is 4. So if I plug this into my formula, I've got mu squared A squared over 4 divided by 4 times A squared over 4. 2. A squared over 2. That's what we had before, sorry. Mu squared A squared over 4. Now if I multiply top and bottom by 4, I get a relatively simple answer for my efficiency of my signal. And if mu is equal to 0, my efficiency will equal 0. And what that means is I'm just broadcasting the carrier. I'm not broadcasting my message signal at all. Okay? So there's no good stuff is coming through. No information, no 447 hertz, no opera singer. If mu is equal to 1/2, you run that through, and that's an efficiency of less than 10%. I'm sorry, slightly more than 10%, 11%, 1/9. Really horrible efficiency, right? So that motivates you to up the mu. You know you can't cross 1, so you might as well say, okay, well I'm going to be doing a perfect job of having my modulation index. I'm going to work really hard to get 1. And so the best I can do is 1 over 2 plus 1, which is 1/3. Okay? If I plot this in the frequency space, I'll just do the ones. My sidebands become simple. They're just tones, above and below. Here's my carrier. Here's my sidebands. And as I vary mu, I'm varying the relative amounts of these three spikes. So if I drop mu equal to 1, then each of these spikes has the same value, and it looks like my useful power is only found in one sideband. It's a very, very interesting observation, because what that tells us is I can broadcast all the information I want in one sideband, increase my efficiency, decrease my bandwidth. That's really that sounds like just a win, just a win, just a win. Okay. Any questions on envelope modulation, tone modulation? One thing I would recommend you do is last time we looked at diodes and diode bridges. We looked at them as rectifiers. And you might go back now with this in mind and convince yourself that if there's my envelope that I'm broadcasting, if I send it through if I send this through a diode and then a low pass filter of some sort that looks like that, then what I'll have is I'll have a rectified signal. Oh, that's a horrible drawing. And then this low pass filter here will connect the peaks and give me my restored signal. Okay? So we talked a little bit about that last time, and I'll just let you think about that here. All right. So that's sort of what I meant by AM envelope. Now I want to get into a little bit more fancy term, a fancier way of propagating, or amplitude modulation. And this will be called QAM, for quadrature amplitude modulation. So, right off the bat, there's this term of art called quadrature. Okay? And if you think in terms of Euler's relationship, e to the I theta is equal to cosine theta plus I sine theta, e to the I omega t is equal to cosine omega t plus I sine of omega t. The difference between the cosine and the sine is that I, which is also the 90-degree marker. And so, if I launch a cosine in, what I'll have is some amount into a system. What will come out is some amount of cosine and some amount of sine. The amount of cosine that I have is the in-phase part. The amount of the sine I have is the quadrature or out-of-phase part. Okay? Now, we think as engineers that in-phase and out-of-phase is too obvious, and so we say in-phase and quadrature instead of in-phase and out-of-phase. Because quadrature is such a cooler word. But that's all we mean. Okay? That's all we mean. So in-phase and out-of-phase. Now, we motivate this exactly the way we had before, which was the fact that somehow if I have this as this is what I've been here's zero frequency sitting out over here. I've got some negative stuff there, But if I just look at what's going on at omega c, this is what we've learned how to do with a single mixer and a cosine. And when we look through the efficiencies of the tone modulation, we realized that we were paying a price. We were transmitting this stuff here, which is really just the reflection of this guy here. It's always symmetric. There's symmetry involved here, so it's always symmetric. So if I know what's going on here, I know also what's going on here. If I measure this, I know this already. And that's tremendously wasteful. We cast it as wasteful from a power perspective because I was 1/3 efficient instead of 2/3 efficient. Or I'm sorry, half efficient. Okay? So that's a problem right there. The other thing that's actually a much bigger deal is this guy here uses far less, half the bandwidth that this guy here does. Okay? Half the bandwidth. Bandwidth is incredibly expensive. If you buy it from the FCC, you get a certain amount of bandwidth. And so if you have that bandwidth and you can figure out a way to use half of it, then you can recycle and reuse the other half of it some other magic special way. And so for the same hardware, or maybe just a little bit more hardware, you can double your revenue if you're a commercial carrying traffic. Or if you want to, you can double your resolution. Or if you want to, you can go twice as far, distance-wise. Okay? Because many impairments happen to scale with bandwidth. So for all those reasons, we much prefer restricting our bandwidth. So we want to restrict our bandwidth saves dollars, increases revenues, lowers impairments. So this is what we want. Redundant and wasteful. That's what we want to do, and that's the goal behind Quadrature AM, is to figure out a way to not do the DSB, not do the double sideband, but to do a single sideband, or a QAM signal. And we have to be imaginative and think a little bit about how this works. Okay? Somehow, if we use a single mixer, we're stuck. It seems like we're stuck with this kind of a picture. Somehow we want to cancel things out. And one thing to motivate that I'm going to start calling things upper sideband and lower sideband. Okay? Upper sideband, lower sideband. Okay? Just again, notation, terminology, vocabulary. And to sort of give you a flavor of what we might be thinking, we go way back to day one, where we say that here's my cosine, plotted in frequency space. Here's my sine, plotted in frequency space. And the eureka moment is to say the phase, the 90 degrees phase shift between a sine and a cosine, the phase can somehow be used to cancel. Okay? That's sort of the eureka moment on this. Now, another way to think about it is a cosine is perpendicular to a sine. That means they're independent. That means they're linearly independent. And so somehow I might be able to use, at one frequency, at 1 omega c, I might be able to use a cosine and a sine at the same time. And in fact, this general line of thinking is actually going to get us through two types of modulations. Today we're going to talk about QAM. Also on Wednesday we're going to go back over QAM and go a little bit further in it. And then we've got 15 minutes, 20 minutes. And then we'll also talk about single sideband, which will be a much more sophisticated, read complicated method of doing almost the same thing. Okay. So today we'll look at the fact that cosine and sine are perpendicular. So let me go ahead and play around with my block diagrams to see if I can come up with something interesting. So I've already decided for noise conditions, for noise, and also for physics of propagation reasons that I want to use a carrier frequency. And what I want to do is I want to be greedy. I'm like Sarnoff or at RCA, and I want to use my bandwidth to get twice as much revenue. So I'm going to say I'm going to have two message signals. An M1 of 2 and an M2 of 2, an M2 of 2. An M1 of T and an M2 of T. And I'm going to split my local oscillator up into two components. This guy here is a cosine of omega ct. So after the mixer, I have M1 of t cosine of omega ct. I'm going to have a sum. I know I'm going to mix this information from my second message signal. Except now what I'm going to do is I'm going to put a delay block in there of 90 degrees. And what that'll do is that'll give me a cosine of omega ct minus pi over 2, and that's going to equal the sine of omega ct. By using the same local oscillator, I know that I can generate a carrier and a carrier at 90 degrees out of phase, because they both come from the same signal. If I'm working at a really high frequency, I have to make sure my leads are about the same length, because it takes time, the speed of light, to move my signal down these leads. So I can't be moving, this has to be small relative to a wavelength, or the error has to be small relative to the wavelength. One of those little practicalities. So now I'll send this guy into my other mixer, and what will come out over here is M2 of t sine of omega ct. And the output here is QAM of t, psi of QAM of t. So this is just playing around and saying, okay, how do I use the fact that cosines and sines are perpendicular Well, if they're perpendicular, if they're orthogonal, the dot product between them, the overlap product between them is 0. So one signal can live on one phase, and the other signal can live 90 degrees out of phase, and they'll never overlap. And that's the premise. We have to prove that it works, but that's the premise. And if that's the case, here's a realization of it. Here's a block diagram that implements that. Start with a local oscillator, so I have the same sinusoid going to both message signals. I keep one alone, I call that a cosine. I phase shift it 90 degrees, so I turn that cosine into a sine. I mix an M1, I mix an M2, I add them together, and that's my final QAM signal. And that final QAM signal then is written like that. Okay. Now, does this work? Well, if I can figure out a way to demodulate this, then it will work. I then will have to look at errors and channel impairments and everything like that, but fundamentally, from a fundamental, will it work? Yes, sir.
So, like, what's that mean to have the two different message signals?
Thank you. The question was, what does it mean to have two message signals, an M1 of T and an M2 of T? Well, what it means is I can charge you money to have a conversation, to broadcast your music, and I can charge you money to broadcast your music. And the people that want to listen to your music can tune the dial to yours, and the people who want to listen to your music can tune the dial to you. Okay? So two message signals means two completely different two completely different streams of data. Twice the amount of commercials, twice the amount of videos, twice the amount of messages, completely independent. So I can watch cute cat videos from you, and I can watch cute dog videos from you by switching the dial. You both can pay me to broadcast your artwork on independent channels, and you don't even know it, because I've recycled that sideband that canceled. That's a good thing.
I'm thinking, like, since M1 and M2 are not the same, that they won't cancel cleanly.
So, let's think about this first for now, okay? This is we don't know if this is going to work, but this is a way of using a sine and a cosine. And in the description, okay, so the question was, since M1 and M2 are unrelated, we don't know that this is perfectly going to work. We think there might be some wiggling around of the phase of the information that's going to pollute one to the other. In other words, we know cosine and sine are perpendicular. We don't know that M1 and cosine and M2 cosine are perpendicular. Okay, that's the question that you have. So, the way I'm answering this is, I'm going to set up a trial system. If I can demodulate this cleanly, so that M2 doesn't interfere with M1 and M1 doesn't interfere with M2, then I'm okay. If I have something else in here that causes them to mix, then I'm out of luck. Okay? But as I've set up the problem, I start with a cosine, so I know I have a cosine going in here, and I know I have a sine going in here. And the way I've set my system up is, I make the assumption that M1 is unrelated to M2. So the fact that they have different subscripts means I'll be able to track M1 through the system and M2 through the system. So if I have any interference, like what you're worried about, it will at least be in my analysis. Okay? To answer this, let's see if we can demodulate this. Okay? To answer this, let's see if we can demodulate this. So the first thing I'm going to do is I'm going to say, okay, channel is perfect. And Lottie says the channel is equal to 1. The transfer function for that channel is equal to 1. So I'm going to say the channel is perfect, and what I broadcast comes into my receiver. Back-to-back test. It seems to me that I want a local oscillator, and that I want it at a particular frequency. So cosine omega CT. Seems to me that I need to use this twice. So that I have access to a cosine omega CT and a sine of omega CT. Now, remember one way of demodulating the AM signal was just to use the cosine term again in a mixer. So what I'll do is I'll take this, I'll split the signal up into 2, and I'll send it into that mixer there. Let me call the output of this x1 of t, just an intermediate signal. Okay? So let me just pause there, and let me just see what the heck I have for x1 of t. Okay? So x1 of t is going to be psi of QAM multiplied by cosine omega CT. Okay? Everyone okay with that? All right, now I'm going to do something that I don't really like to do, but I'm going to follow Lottie's convention. It's going to stress you out. It stresses me out. And for some reason, I'm going to add an extra factor of 2 in there. Okay? If I have access to a volt of cosine omega CT, I certainly have access to 2 volts. Okay? So I'm just going to put in an arbitrary factor of 2 as a level gain on that. Lottie uses it all the time. It makes the math simpler. Lottie is a very good theoretician. I'd be worried about 5 orders of magnitude of loss in the channel. He's worried about a factor of 2 to cancel with the trig identities. Okay? It's all right. It's much neater this way. So there's an extra factor of 2 floating around in there as well. I really don't want you to stress out about that. So I have 2 m1 of t cosine of omega ct plus 2 m2 of t sine of omega ct. That's my QAM signal. And I multiply that by cosine of omega ct. So now we multiply through. think I have all the terms there, do I? So now I have a cosine squared, which divides out into an m1 of t plus an m1 of t times cosine of twice omega ct. So cosine squared is equal to 1/2 plus cosine of twice omega ct. So that's why you introduce that weird factor of 2 to cancel those 1/2s. And then this cosine here, this sine times cosine, gives you a sine of omega c plus omega c and a sine of omega c minus omega c. So this term here gives you an m2 of t times the sine of twice omega ct plus m2 of t times the sine of 0 omega c t. Okay? The sine of 0 is 0, right? Now, we have 3 terms. Which is the term we want? Any of them? That's right. There's my message signal, and that's what needs to come out of my demodulator. That message signal is the one that needs to come out of my demodulator. What do I do about these guys here?
Filter.
What kind of filter? Low pass filter. Low pass filter will be fine because I don't want to destroy what's at baseband. Okay? So just a nice low pass filter on x1 of t, and now the output of this will be m1 of t on the output of that. Where's m2? M2 got canceled. Low pass filter, low pass filter. Okay. So we recovered this. We with that extra little bit of filtering, we recovered it. Okay. So what I'd like you to do tonight, or maybe tomorrow, not too long, is to show that if I send this guy into here, I'll have an x2 of t. And then if I play the same game, low pass filter it, what will come out here will be an m2 of t. So to do that, you'll write down, this is all you need, right? This much space is all you'll need. You'll have x2 of t is equal to 2QAM cosine omega, sine of omega ct. The only thing that will change will be your trig identities, your various trig identities. And with that trick of low-pass filtering, just convince yourself or see that you get an m2 of t out. Okay?